Okay, so I guess I will start. I'm Ilyes, and I'm currently a master student in Cambridge, but I'm also studying at ENS, Paris-Saclay, and I'm doing both chemistry and more ML, machine learning in my, but more on the math side in my master. And David, if you want to.
Yeah, I can also say a few words. I'm David, so I'm also in Cambridge, doing currently my PhD, and my background is in natural sciences in undergrad, and then I did an MPH project in more sort of natural language processing and applied to chemistry, and then I jumped to do sort of molecular modeling, and then sort of force fields and fitting the energy of molecules. Sort of first with linear methods and then with graph neural networks. That's work we have done with EDS.
Okay, I guess I can start with the
just to say that I think just one more. So I mean, it's kind of a reading group. So I think it would be great if people could people could interrupt us during as we talk, not just at the end.
Yeah, please feel free.
How we usually do it, but thanks for the permission.
Yeah, so today's talk, well, not talk, but conversation is about MACE, a recent paper, and I call the talk higher order if we equivariant message passing fast and accurate force field, because it's the title of the paper. And I will explain all these words in more details. So first, because this is an ML reading group, I want to have more ML perspective on the subject than just the chemist. And what we are really doing is actually much broader than just chemistry, is finding a good representation of cloud of particles in interaction. And this is really what we are aiming to do. And particle clouds interaction are everywhere in physics and chemistry, but even beyond. And the goal is really to understand the properties of this cloud of particles. And this could be anything like electrons in our case, but it could be or atoms, but it could be also quarks or gluon or anything you can think of. This is just a set of points. And the properties of these points usually that they are embedded in a certain vector space. And each of these points has an associated positional quantity, which lives here in RD, but it can be a vector space. And they could have also other type of quantities, like for example, in chemistry, you also have some chemical properties, like what kind of species it is. And you can gather all that into a state, here sigma I, and each point in this point cloud will have a state of all the other features and the positional features. And furthermore, you can also have enforce a topology on this point cloud, because you know in some case that the physics is mostly short range, so you can have a cutoff distance, but you could have other type of clustering algorithm. Usually we only use the locality assumption. And so this form a topology, and thus you have a graph on this point cloud. And what you want to do is to find representation of these point clouds. And usually you want them to be equivariant. Why you want them to be equivariant? Because the underlying interaction between the points in this point cloud obey a certain symmetry group. You know that all the interactions in physics have some underlying symmetries, and you want thus to your representation to be faithful to these underlying representations. And the goal is really to approximate regular function from the space of all states in your point cloud to a certain target vector space that are both G equivariant, so your group, and also permutation invariant, because by representing your point cloud on a computer, you actually create an additional breaking of symmetry that actually is not really in the physics, which consists of the labeling of the particles. And you want this symmetry to not interact with your representation, so you want to be permutation invariant in the end. And interatomic potentials or force fields, so what we are doing with MACE, is just one type of this mapping, that is the mapping from the point cloud of all atoms to scalar quantities, which are rotationally invariant. And these scalars will be interpreted as energies. And we know for a sufficiently large set of Lie groups that we call reductive Lie groups that you can form a complete basis of this representation. So there is a systematic way to create that. And you can approximate any of these regular enough function by a linear combination of these bases. However, and in the case of O3, this basis was actually formulated in full precision in the atomic cluster expansion ACE that David will recap in more detail after. But one problem of this complete basis is that it's too large. So what you need to aim, if you want to find something computationally efficient, is a kind of sparsification or decomposition or reordering of this set of complete bases that maximize efficiency and accuracy. So it's really what we will be aiming with MPNNs. Yeah.
So complete basis of equivariant representations, you're saying this always exists?
So as soon as you have a reducible Lie group, which is most the case in physics, actually you can show that any functions regular enough, but I mean regular enough is continuous function, so usually, but you can, and also local, because you have local approximation and stuff like that. Under this precise assumption that you can find in the ACE paper, you can actually construct this complete basis for any kind of thing. So but really it's quite, yeah.
When you say large sets, what do you mean?
So
actually it's infinite.
Yeah, exactly. I was just going to say that, like, all this means is that we have a machinery to create features which form a linearly complete description of, say, atomic environments, so 3D point clouds. But like, just the fact that we can create these functions doesn't mean that they are optimal. And I think what Ilias talked about with MACE is that we think that MACE actually is much closer to optimal kind of functional form.
Yeah, if you're doing this, just creating this basis like that in a most naive way, it won't be computationally efficient and you won't reach very good accuracy or very good efficiency with that. So it's more useful in a theoretical perspective than really in a computational sense. So it's really what the aim of the talk is how to do that in a more efficient way. And the case that we're interested in is the O3 group, so the group of all rotation in 3D space. Because chemistry, the underlying physics in chemistry can be approximated to some interaction that are invariant to the O3 group. And what we are trying to do is interatomic potentials. And so here a bit of chemistry. I'm sure most of you know about that, but usually when you want to compute properties of molecules, like energies, you need ab initio computation that start from first principles, but they are very expensive. So the idea is just to remove the electrons and just parameterize the energy of a molecule by just the position of the atom. And this has been very successful in the past. Empirical force field have been very useful in biochemistry and other applications, but they are usually not accurate enough for a lot of quantitative applications, and they are also not reactive. And about 10 years ago, machine learning force field emerged as a way to achieve more accuracy, usually closer to the, or even at the ab initio computation accuracy, and also they are reactive. So you can do real chemistry with them. And it's a very simple RD. What are machines?
Yeah. Christian is asking, what does reactive mean?
Yeah, I can answer that very quickly. So I think what it means is that in empirical force fields, you have to say a priori before you do a simulation which atoms are bonded and which are not bonded. And this is fixed during the simulation. So, you can't break or create bonds during the simulation. Whereas in machine learning force fields, we usually use smooth cutoffs. So your graph topology can change during the simulation as atoms get closer or move further apart from each other.
Yeah, exactly. So you don't have a fixed functional form. And usually the empirical force fields are very, very well parameterized. but you cannot break this parameterization or they fall apart. So basically everything is fixed, no reaction. Yeah, I was saying, yeah, ML interatomic potentials are actually a very simple idea. It's just to fit a parametric function. It can be anything, a linear model, a norm network. That is a function of two things: the atomic positions, R, which is just a matrix of size 3 by n, and then the chemical elements. And one central assumption is the assumption of locality that gives the topology on your graph. And this is given by a cutoff radius that creates neighborhoods. So this is the Ni. And you assume that your total function can be approximated as a sum of local terms, which are called site energies. So these are the EI that are only a function of a certain set of neighbors. And the hope is that you feed that to a reference data, can be a GFTE, couple cluster, and you hope to have the reference accuracy, but without the explicit treatment of electrons, so it's much faster. And usually one way to approximate this local site energy is to use body order decomposition, just a Taylor expansion of this thing. And then your real goal is actually to approximate any term in this expansion, the V's. One thing that has been very successful in the attempt to do ML force field is the symmetries, And respecting the symmetries of the entire physics is essential for accurate potentials. And the symmetries we are talking about are the translation symmetry, rotation, which form the E3 group, and the permutation symmetry that I've discussed before. So the rotation symmetry, I think most of you are familiar with spherical harmonics. Yeah.
Like just translation plus rotation is SE3, right? And with reflections, we have E3.
Yeah, with reflections for E3. But usually our models are also reflection. Well, rotation is proper rotation or non-proper rotation. So actually the reflection are part of the rotations. Yeah. So here you consider all the type of rotation, which makes it E3. And so you have the spherical harmonics that are the basis of the irreducible representation of the rotations. And then the translations, you forget about it because you just consider the pairwise distances, which are translationally invariant. And the spherical harmonics, you know how they transform according to the rotations. So when you take products, you also know how to symmetrize them. But I will go in detail later exactly what this means. And machine learning interatomic potential as the field has led to a growing number of new architecture the past few years. And it has been quite a zoo of new things, but one very big constant is the presence of the E3 equivariance. So all the successful machine learning potentials the past years have always been E3 equivariant in some way. And particularly notable among these are the atomic cluster expansion that I discussed earlier, that unified many of the previous ideas around atomic density-based descriptors that was proposed by Ravdrov, and MQUIP, which is a message passing neural network with equivariant features that showed really a new state-of-the-art performance that was proposed last year or in 2 years. And now, today we want to talk with David about MACE, which is a new kind of equivariant message passing neural network that aim to resolve some of the problems of the previous approaches. And a quick recap on what are message passing potentials. And I know most of you are familiar with that, but MPNNs are just graph neural network, and they map label graph to vector spaces. And in the case of interatomic potentials, the labels on the graph, we call them semilocal states. And these semilocal states are composed of 3 features. The first one is the position of the atom, I. The second one is the set of fixed attributes that usually in force field we take only as the chemical elements of this atom I. And then HI is just learnable features that is meant to be updated during the algorithm. And you concatenate that, or you gather that into one thing that is called the semi-local state. And why we say it's a semi-local state is because MPNNs are recursive algorithms that aim to extend the receptive field each time you do the recursion. So in most MPNN with 4 or 5 layers, you can end up with receptive field of beyond 20 or 30 angstrom, which is no longer strictly local, but we call them semi-local. And MPNN potential have really 3 phases. The first one is the message construction. So the way you do that is that you embed the state of 2 neighboring atoms that are connected by edges. This is sigma I and sigma j, with a function mt, and then you gather all this embedding around the around all the neighborhood of I. And then this gathering can take several forms, but you can think that just a sum in most MPNN. And this form your message on I, mi, at each, and you do that at each iteration. And then you update the state of the atom with an update function that is a function of both this gathering message and also the state of the atom, the previous state. And thus you create a new feature, hi at time t+1. And in the reduce phase, you map all the states of the atoms to a quantity, the readout quantity, which is in our case the site energy, EI, the energy on atom I. And these are the 3 phases. And as I said, we will aim to construct equivariant MPNNs. Here I forgot about the translations because they are not really explicit. And what this means of equivariant is that the internal features of your network should have well-defined transformation under the rotation of inputs. And if you take a rotation matrix Q and you rotate the distances, the positions as input, then you know how the internal feature transform because you know the representation of the group. This leads to symmetry labels. I think you already had a lot of talk on equivariant networks in the O3 group, so probably all know what are the LMs labels, but they just index the representation of the group. And thus you know the corresponding Wigner matrices. And this is just what it means, that you keep track of how your internal features transform according to the rotations. And what are the current limitations of machine learning potentials, and in particular MPNNs today? First, the biggest limitation is actually most equivariant MPNN, well, all of them, pass only 2-body messages. So this leads to a direct relationship between the number of layers and the expressivity of the network. So 2-body means that this function mi can be expressed as a sum of 2-body terms, and this 2-body in the sense of 2-body of the states. And the previous approach is proposed to do invariant many-body messages are very expensive because they sum explicitly over triplets and quadruplets. So you have a large sum, and this sum scales very badly because it scales as a power of your body order, actually.
So just to put some names, so this is like JamNet and DimeNet, I think, who do
exactly,
this like invariant many-body message passing by incorporating angles, for example, as features. But to get the angles, you need to actually look at all triplets in the environment.
Yeah. And then
there's a
MACE.
question. What does expressivity mean? Yes, we have this question.
Yeah. So what we mean by expressivity is that you want to approximate a function of a certain type. And in particular, you're doing this body order expansion. So basically, one kind of expressivity that you need is how high you go in this body order expansion. So how can you approximate function of higher and higher correlation? And the only way for 2-body message passing networks to increase this kind of expressivity, meaning how good they can approximate function of high correlation, is just to stack layers. And this is why there is a relationship between the number of layers and expressivity, because the only way to increase the correlation order of the total representation the network is constructing is by stacking layers. And so you have a direct relationship this way. But in a MACE, which is the new architecture I'm talking about, it's an MPNN that constructs equivariant messages of arbitrary high body order in an efficient manner. And we show that.
Ilias, can I just reply to one comment? So just to clarify this, what does body and body order mean? So what you have to think about is when we say that we have a 3-body message, that means that the message, the value of the message depends on the central atom and 2 of its neighbors' simultaneous position. Okay, so in normal MPNNs, you have the edge features, and the edge feature depends on the central atom and 1 neighbor. And then you have some kind of pooling operation on that. But if you have a 3-body message, then the 3-body message depends on the central atom and the simultaneous position of the 2 neighbors. And then if it's 4-body, then simultaneous position of 3 neighbors. Okay, so this is how we talk about body order.
Yeah, exactly. And it's really key in the representation of many-body system, because the many-body system are governed by their many-body order. And using 4-body messages, which is actually quite high, the required number of message passing is reduced to just 2 instead of 4, 5, 6 for order. And so this leads to a faster network, but also more parallelizable, because the more you grow the receptive field, the harder is it to fill all the required atom into a single GPU or CPU memory. So let's dive into the MACE formalism. And the first thing of any MPNN potential is the message construction. And the way the message construction is computed is as a many-body expansion of the states. And so this is what David just said, is that you have different terms, and each term corresponds to a different body order. And if it's body order just 2, then it depends only on 2 atoms, states, and 3 on 3, etc. And the idea is that we know how to approximate each of these terms by a linear computation of a complete basis of many-body equivalent features, inspired by the construction of the atomic cluster expansion. So this means that any of these U terms, you know that you can achieve them up to any accuracy by just a linear combination of something. And so the idea is to leverage that to approximate each of them. And the way this is done is first by constructing permutation invariant basis. So it's a basis of all 2-body permutation invariant features. And these are constructed the usual way. It's very familiar, if you're familiar with ML potentials, it's just a product of the radial features and the spherical harmonics. The radial features are just a function of the distances between these 2 atoms, and the spherical harmonics are a function of the vectors. So they have a geometric information. And then you also product in the previous H features. And this creates these A features that are a complete basis of 2-body permutation invariant functions. One thing important is that the invariants come from the pooling of from this sum. So here you sum over all the neighbors, and so obviously when you do the sum, it's a permutation invariance. So now the permutation invariance symmetry is checked.
And sorry, maybe just Ilias, just to remark on the C, because so basically what you have here is this HTJKL to M2 is the feature on your neighbor atom. And that feature is actually a vector feature. So it can be like different spherical harmonic representation. And so you take a learnable kind of fraction of that with this W, and then you take an equivariant tensor product of those neighbor vector features with the kind of with the spherical harmonics of the displacement vector between the neighbor and the central atom, and that is symmetrized using these Clebsch-Gordon coefficients C. Okay, so that's what this equation means.
Yeah, in the end, the A, you know, their indices L3 and 3 because you have symmetry with them. So you have kept track of how they transform. And then the key operation of MACE, and this is something David will expand more about just after, is the partial tensor product of these permutation invariant features and then the symmetrization. So this is really the key operation of MACE. So basically, you have these A features, which are permutation invariant and two-body. And then you take a tensor product, this product from 1 to nu. And this tensor product is partial because you don't take product on the K channel. So you only take products on the LM. And then you apply a projection operator that we call the generalized Clebsch-Gordon that just projects from the space of the tensor product space after the product here to the space of equivariant features. So it just maps the tensor product space to LM equivariant features. And this is really the key operations, and it constructs these B features, which are a complete, and David will say how you can show that they are complete, a basis of equivariant features of a given new correlation. And then, because you know these are complete, then you can approximate your message as just a linear combination of these B bases here. And then,
So,
yeah.
Shall we stop here for questions?
There is a lot of questions? Oh.
I don't know. I thought maybe we could encourage people to ask questions.
Yeah.
I think if people struggle with the paper, this might be here.
Yeah,
So
I guess it's really the key operation.
Anyone wants to ask some questions here about this? I mean, there's a lot of indices going on, so
yeah,
if you want,
maybe I should explain that. So
yeah, okay.
Can I put my mouth? Do you see my mouth or no?
We see your mouth.
Yes.
Oh, great. So these LM indices are just the spherical channels indices. And this is what linked to David's remark, is that we know how this space is transformed. So basically, if you take, for example, LM equal to 0, 0, then you know that these A features are just scalars, invariant scalars. And if you take the L to equal 1, then this A will have 3 components, the L11, L01, and the L-1. And so this LM indices this representation. The K is the channel. And so all these on all these networks, you repeat in parallel the same operation over a large number of channels that you only mix linearly. And so this K is the channel index, and yeah, there are typical values. Usually we use 128 or 256, something like that, channels. And this W just mean that you have weights. So these are learnable weights, and you take a learnable linear combination of A features having the same L symmetry, because you don't want to break equivariance, and you take this linear combination over the channels. Then the product, you see the psi here, goes from 1 to nu. So nu is the correlation order. So it's how high you want this representation to be correlated together. So the number of products you do in your tensor product. And you see the psi is only indexed into the LM and not the K. So you don't take product over K. So this is very important. You just take product of LMs. And then this bold LM thing is just the tuple of all the LMs you have been produced. And this C is really just a projection matrix. And you tell him, you tell it what kind of tuple you have created, what kind of bold LM you have created, and the kind of target symmetry you want. So these are the big LM, and it tells you how to symmetrize it. So just you give it the tuple and the target you want, and it gives you the projection from that. And it's really a classic projection operator. And this eta, which might be the most tricky indexing this, is actually a very rough index that this is all the kind of permutation and coupling of this LM tuple you can do. So actually you have a lot of paths to create the same LM representation. which means that you have a lot of equivalent paths in the due to the symmetrization, and this indices all the paths you can create. So it means it indices all the kind of non-equivalent B features you can create. And this is because this eta exists because you do a projection from the tensor product space, which is a very large product space, to a subspace, which is the subspace of only equivariant features. And obviously, this subspace and permutation invariant, obviously, this subspace is smaller. So you will have equivalent things going on. So you need to sum over this equivalent. Well, to make sure you have this equivalent. And the sum over these equivalent things takes place here, actually. So here, these weights have an eta. Okay, I hope it will be clearer.
Just one small clarifying question. Compared to kind of the full tensor product that would include kind of taking the product over the channels K as well, what is there kind of an intuitive way to think about, like, is this something like taking somewhat of a diagonal network, or like kind of limiting the interactions between channels?
Exactly.
You can spare your question for like 5 more minutes. I will give a full theoretical justification for that. That's basically my part of the talk.
Perfect.
Yeah, but we have quite an understanding to why it works. So yeah, it's a diagonal thing. Yeah, hopefully, yeah, it is. So yeah, David will go in depth into that. So I guess I can just finish that before David takes over. Then when you have created your message, you update your features by just a function of the previous state and the message you have just created. And then you need to map the state of all atoms to energies. And in MACE, the particularity is that you read off the state at each layer, and then you have a readout function for each layer, and each layer will be a term in this body order construction. And because MACE, as you've seen, has no pointwise nonlinearities in the message construction, then it's very nice because you can see that these terms are actually body ordered of increasing body order. So you can really think that as constructing explicitly the body order expansion that we talked about at first. And to make sure that we really do that, all the readout needs to be linear, except the last, because the last, we think about it as a nonlinear correction to the body order expansion for it to converge. So basically, all the T-1 readouts are linear, and then the last one is just a nonlinear correction. Usually, MACE architectures are just 2 layers. So you have one linear term, and then you have a nonlinear correction in the second term. And yeah, I guess David can go about you have some slide about this tensor product.
Yeah, but maybe I can just address very quickly the question in the chat. So the question is basically asking that if we have a four-body term, and there are more than 3 atoms, so more than 3 neighbors, then how do we select? And I think this is super important, that what we don't do is we don't actually sum over all of the three neighbors. So what we do is we sum over all pairs. So you just take the edges and you sum over them. And then what you do is you form these tensor products on the central atom. And this tensor products on the central atom will kind of implicitly form a basis for the 4-body functions. So we don't create 4-body features by summing over 3 neighbors, but we create 4-body features by summing over all neighbors together and then taking tensor products. And this is
just
where like
swapping the
efficiency comes from.
Exactly, because it's like mathematically it's just swapping the product with the sum, and doing the sum first and then the product is more. And the reason it's more efficient is because you have much more edges than nodes in a graph. Well, usually in typical chemistry graph, you have much more, like 10 or 50 more edges than nodes. So you reduce by a factor of that, the cost.
Okay.
I think there is another question I've seen on the layers. Why do you separate the last layer's features? What is the intuition beyond the experiment performance? So, well, first, it works well. And second, what I explained is that we really wanted to have a body order expansion. And so as there is no nonlinearity in the network, in the message construction, then we know exactly the correlation order. If you put a pointwise nonlinearity in MLP, then usually if you do a CLU or ReLU, then the Taylor expansion of this nonlinearity is infinite. So you cannot really say you have a body order expansion because your Taylor expansion is infinite. Whether all the output of MACE has a finite Taylor expansion with respect to the positions. So this is why we really separate the last, because we just think of all the previous term as a really neat, like proper body order expansion. And then the last layer is here to help the convergence. And in our previous paper on botnet, we have shown that this kind of architecture really learns some kind of decreasing terms, because you expect these terms to decrease, because if you have a convergent body order expansion, the higher you go, the smaller the terms should be. And actually, when you observe that, when you check that numerically, then it does happen. The first terms are bigger than the second, etc.
So was there one more question by Dominic or no?
Yeah, so I just want to clarify a few things, just to make sure I understand everything. Like the R terms and Y terms are taken from like the from spherical harmonics, right? Like, and you try to like how does the learned weight affect these functions? Like do you learn a weight for each part, like for each set of for each element of the set of spherical harmonics, you learn a weight associated to it? Or like, could you explain a bit more like what this kind of function does?
Yeah. So this R function is the radial function, and it's actually a learnable function. And you learn a different radial for each type of L in the YLM, and for each type of L in the H, and also for each type of output L. So you have these triple indices here. So
but
really,
how do you make this R learnable? Like that's my question.
It's just
so
it's a Bessel base. Yeah, it's a Bessel basis. So you expand that in the Bessel basis, and you have a number of bases. So this is very standard. It goes back to DiveNet and Equip.
Okay.
You have and then you have 8 or 10 Bessels, and then you take a linear combination of that with learnable weights. It is just
okay, perfect. And do you kind of regularize such that like the first few terms have higher weight associated to them, or you just learn any kind of possible weight and you then like observe that the first terms have higher or more important than the other?
Yeah, so we don't explicitly regularize, but there are some normalization inside the network. So this is the lambda here. I didn't put here, but in MPNN you have a lambda, and usually choosing how you do this lambda changes the scaling at each iteration. And because our lambda is 1 over the size of this set, so the average number of, not really the size, but the average size of this set, so the average number of neighbors, and it's not 1 over the square root, but 1 over n, then really it decreases with the number of things. With the number of message passing, it decreases because each time you will divide the norm of your message by the square root of n. But it's not really an explicit regularization. It's just done at initialization. So we don't explicitly force anything really. It just happens after training. We have regularization, but the only regularization we have are over these weights here and these weights here. So here we apply standard L2 regularization, and we find that to be very, very important.
Yeah. So why are you choosing to not regularize the weights, to give more weights to the first terms of the function, since it's expected that they are?
I think I think the physics dictates that we don't need to regularize it.
Yeah.
Yeah,
I think
sure,
if you have it naturally, it's fine, really.
Yeah.
Because obviously, so the less body order the representation has, the most chance it has to capture interaction of high energies. Because the most energies in physics are the two-body energies than the free-body. And so if naturally it captures that, it means that really it's forced to capture two-body interactions. And the only two-body interaction you have in your data are really of this strength. So I think really, yeah, the body order itself is really already regularizing that in some sense.
No, for sure. So like you're saying basically the data reflects that, but wouldn't it help in regularization? Sorry, in generalization, if these were regularized, or you think?
Well, yeah,
I think as a rule of thumb, you want to get away with as few hyperparameters as possible. So if you don't need to regularize something, just don't.
Yeah, and also,
well, you don't know if you need until you try. Like, but since I believe with the higher orders, you get more noise in some sense, then maybe the network can overfit more on these. But at the same time, like I don't have any concrete evidence that it should help. I'm just asking.
Yeah, but to reassure you, I have tested probably all the type of regulation you can do, and this is the best one. So if you want empirical evidence, I have tested those. So I've tested changing all the regularization of each weight, and really it's very bad to regularize every weight except these two for some reason that we don't fully understand, but yeah. One thing, there is some implicit regularization in the data, that's sure. And also to note, it's really, usually in this MPNN potential, there is no regularization explicitly. So if you look at Nequip or Allegro or DimeNet, usually, at least for Nequip, I'm sure, there is no explicit regularization term. And it's usually with deep neural network, it's quite better to not include explicit L2 regularization for deep ones. But because our network is a bit special, it's a bit more wide than deep. And this is really the specialty of MACE. It's only 2 layers, but it's quite wide due to the transport project. Then we actually regularize a bit. Okay, I guess we can go on with
yeah, thank you. You can go on with the presentation.
Yeah, I think I might be actually very fast because and then let Elias to show the results. But what I just wanted to kind of very quickly and briefly show is that we actually do have a lot of theoretical justification for MACE. So MACE wasn't born out of ad hoc experimentation, but actually there's a lot of rigorous stuff going on there behind the scenes. So I thought I'd just very quickly summarize that there is this atomic cluster expansion, which gives these complete set of basis functions, and then how kind of message passing and this tensor reduced architecture are both kind of helping MACE be this state-of-the-art potential in kind of speed and accuracy. So first thing first is just very basic maths. If you have a complete set of basis functions on some space, so say on a these radials and spherical harmonics, give a complete description of any function that depends on the position of one atom, right? Because you have a complete radial base and a complete angular basis. And then if you form tensor products of these basis functions, so tensor product meaning just these products, and then you take it over NLM over all of the channels, then you get a tensor product basis. And there is a kind of a theorem, which is well known, that any regular and local function will be in the span of this tensor product basis. So all it says is that by forming these tensor products, you can represent any function. You can get a full basis of the tensor product space. So in this case, having a complete set of functions for the position of one neighbor And taking tensor products, we get a complete set of functions for a position of n neighbors if we take an order n tensor product. So this is kind of the basic background for maths. And then really ACE, what ACE does is ACE starts by having a one particle basis functions, which are essentially edge features. And then you take the edge features and you pool, you do a summation. And here we actually keep these indices. So Z is the chemical element, NLM are radial and angular features. You sum over the neighbors, and then you form the full tensor product to form the full tensor product basis function. Okay, and this will be kind of new body, if you like, or nu plus one body, because you count the central atom. And then you do some rotational symmetry just by doing a projection using these Krebs-Gordon coefficients into a symmetric subspace. And that is these B basis functions. So this is really the ACE construction. And it's kind of, this is really this simple, how you form a complete set of symmetric features in this 3D space. And so completeness comes from this tensor product structure, really. So you have this generalized ACE output, which in this case is, because it's linearly complete, so I actually am showing here a linear model on these features. So I hope this is vaguely clear. And now we have to think, okay, what goes into this? So this is what we call a linear atomic cluster expansion, and this is what I did in the first year of my PhD, and it's pretty good. So you can actually fit models, but it's not as good as something like MACE. And the question is why? And I think what I really like in this atomic cluster expansion construction is that it provides kind of a complete set of features with controlled approximation parameters. So what does that mean? It means that there are kind of three things that goes into this atomic cluster expansion construction. One of them is a cutoff. So if you take an infinite cutoff, so everybody is a neighbor of everybody, then you get a complete description. Then there is the second approximation parameter, which is the maximum body order. And then the third one is where you terminate your one particle basis. So it's kind of like an Nmax and an Lmax. So the how many radial features you take and how many angular features you take. And the MACE, basically what MACE gives is you can think about MACE as an efficient reordering of these basis functions. So it really, MACE manages to pick out of these complete set the ones that are the most relevant. And it has this tensor reduced structure, which increases its efficiency. So I just very briefly show what I mean. It's 2 more slides. So sparsifying the full basis via message passing. So what I mean here is that message passing is different from having a local model in the following way. So let's think about local models like ACE or Allegro for this is also another local model. And you have a central atom and you have kind of neighbors. And you take all neighbors within a cutoff radius. So here, for example, for 3-body, you take all triplets like that. And then the site energy will depend on the simultaneous position of these 2 guys, which is fine. But it will also depend on the simultaneous position of these 2 guys. And that is really not physical. You wouldn't expect that the simultaneous kind of positional correlation of these very far apart atoms should matter. So what happens if you actually do message passing? You have a smaller cutoff, and then you take atoms within that cutoff, and then you do another message passing expansion operation, and then you take these 3-body features, but you only form the connected 3-body features if you do message passing. So what I mean here is really 2 times 4 is not equal to 8. So doing message passing is actually an efficient way of finding the physical clusters, or the physical kind of connected clusters in this way. Does this make sense? So what we can achieve with message passing is really it can pick out the physically most relevant basis functions out of the full complete set of features. So that's why we think that message passing is a very good kind of idea to do. And then the tensor reduced structure is the second one. This is something that should be on arXiv tomorrow. I think we have already submitted it. So this is not really almost published work. So what we can recognize is that the parameters of this linear ACE construction is actually a symmetric tensor. So it's symmetric under kind of swapping of these kinds of indices. And what that means is that for any kind of symmetric tensor, we can expand it as a sum of products of rank 1 tensors. So this is like kind of basic math. And this expansion is actually exact for sufficiently large k, because by truncating the one particle basis, we actually only have a finite set of C's. So we can actually write this down, this kind of expansion in terms of rank 1 tensors exactly. And then we can write it in component form. And what we get is in component form, we have the full A. So this is the A's basis functions, which form a complete set of features. And we can write that out in this way. So basically you have this sum over this case. So those are kind of channels. So you sum over the channels and you have these products of weights. So these products of weights are essentially the product basis that we had before. So what we have here is really kind of a rigorous derivation of these embedding channels, and you don't take the tensor product over the K channel. So you have this kind of, we derive using this symmetric tensor decomposition of the full many-body features, a form which has embedding channels and which has this low rank structure of not taking the tensor product over the embedding channels. So this is what I mean, that MACE is kind of very systematic in this way, because MACE really is a convergible systematic approximation of the full set of features possible. Yeah, and then you can actually do the full derivation that is in this paper that I'm referring to, where you actually find that it all adds up very nicely. And you kind of recover the MACE kind of central equation that Elias was talking about as well. So I'll not talk through this. So the key take-home points is 3. First is that this atomic cluster expansion is a complete set of features of m-body functions. The second is MACE is an efficient and systematic functional form. And the third is that this message passing provides a sparsification of the full basis. And with that, I want to just show 3 papers that you might want to look at. So this design space paper, which we wrote together with the Harvard group of Boris Kozinski. And this contains these ideas of message passing being a sparsification. And this, okay, the MACE paper, and this tensor reuse atomic density representations paper that we wrote with James, a postdoc in our group. And this paper is that contains actually the kind of very detailed derivation of these symmetric tensor decompositions and how you can obtain kind of MACE from the full basis. Yeah, I think I'll stop here. But yeah, this was the kind of, okay, maths part of MACE. If anyone has any questions, I'm happy to take at this point. Or Elias can just quickly show a few bold columns.
Yeah, I can show the results quickly. I don't know how much time we have.
We're not tight, like we usually, it's nice to maybe have a conclusion at 12 for like people that have to leave, but in principle we have as much time as you have.
Okay. So let me just show some results, because no, David has covered math. So what about how it does? So the first result is we are claiming that MACE dissociates the expressivity of the network from the number of layers. And the way we show that is we took this 3BPA dataset that David created that consists of training at low temperature and then extrapolating to higher and higher temperature. And we plot the accuracy both in forces and energy with respect to the number of layers. And you see that MACE in purple converges to its best accuracy in just 2 layers, while Nequip and Botnet, which are statistical 2-body MPNNs, takes actually much more layers to converge. And this is quite, well, you can explain that because actually the 3BPA molecule is quite small. So if you have a 5 or 4 angstrom cutoff, actually after two layers of MPNN, you already have covered the full length of the molecule. So actually what Nequip and Botnet are creating is just body order and not really semi-local information or larger accepted field. So they struggle because of this 2-body nature. I see a question here.
Yeah, if we look at not number of layers, but kind of computation cost, if that's kind of easy to quantify, do we see similar trends?
Yeah. So basically, as we said last time, when you create new body order with stacking features, layers, you do the tensor product on edges, while in MACE, you create higher correlation by taking tensor product on nodes. And because you have much more nodes, much more edges, sorry, than nodes, actually stacking layers is not the optimal way to increase the correlation order. And so you have if you want to look at the prefactor between MACE and Nequip, it will be a function of the average number of neighbors and average number of neighbors in the graph. And I have a graph showing that just later, plotting that. Then one thing that was very cool in the Nequip paper were the learning curves. So it's a way to study data efficiency. And the way you do that is just you plot the number of training data as of the accuracy of your network. So here is just the absolute error with respect to the number of training data. And then you know that the log of that will be a constant that is only a function, should be only a function of the network itself architecture, because the modern neural networks show a power law in their learning dynamic. And so this constant is really a constant of the architecture, and the better this constant here, the better the slope, the more data efficiency you have. And here we plot by tuning the hyperparameter of MACE, so both the correlation order nu and the equivariance L. And you see by increasing the correlation order but not changing the equivariance of the message, you have better and better data efficiency. So this is here. And then on the other panel, you see that by increasing the equivariance but not changing the nu, the equivariance, you also gain data efficiency. So this will be standard Nequip or botnet MPNN. So two-body, nu equal 1 is two-body. And here you see that when you saturate the correlation order, so you have nu equal 3, but you increase the correlation, the equivariance, you don't change the slope. So you shift it, but you don't change. So it doesn't really add new expressivity. And this is possibly because the 3-BPA, so the molecule we are looking at, aspirin here, the molecule we are looking at is quite small. So just 4-body is actually very expressive already.
Just here, I just add the one thing. So basically what we have is the L equals 0, nu equals 1 is basically SNAT. So that is a two-body network that is invariant. And that is actually, it has been shown that L equals 0, nu equals 1 is unable to resolve all distinct chemical environments. So you can come up with physical structures that the SNAT will always give the same prediction for, no matter what. And they are physically distinct. And what equivariance does on the right panel, it helps lift these degeneracies so that the things that are different will be genuinely different. But what we show is that basically once in the middle panel, once you have high body order, then you don't have these degenerate structures anymore. And then equivariance doesn't add this extra resolution.
Yeah, but this probably will be data dependent. And this is why in MACE it's both high order and equivariance to get the most of both. And actually, this is how you get the best accuracy, is both adding geometry information by high order and equivariance. Okay, and yeah, it's nice also because here you can see a lot of the design space. I will talk about this other paper, the design space, but here, as David mentioned, L equals 0, nu equal 1 is net, and then L equal 2, nu equal 1 can be Nequip or botnet. So it's really different hyperparameter, and you can navigate the design space like that. Some benchmarks. So obviously you need bold columns to publish to ML conference. So we did some standard benchmark. It's not, MD17 is not really the most interesting. Actually, to me, it's quite saturated, but we show that MACE can have a similar performance to other state-of-the-art method like Allegro and Nequip. But because it was not really interested, what we tried is to come up with a harder test. And basically, we took only 50 samples from MD17, not the full 1000. And then we trained on these 50 and tested on the rest. And here we see that the comparison between MACE and Nequip is a bit bigger. And it shows that MACE is a bit more data efficient. But the most interesting thing for us as chemists with David is the extrapolation, obviously, and also the speed. And the FreeBPA dataset is really the best for that right now, because you train on 300 Kelvin, so you sample a very narrow space of your conformations, and then you test on higher and higher temperature. And here we show that MACE really achieves quite a significant improvement on other methods. And what is very interesting is that even the passing only invariant message, so L equals 0, already yields quite good extrapolations. And L equals 0 MACE is really is quite fast, because the tensor product on edges is very simple, and so you gain a lot of speed. And this is why with MACE you can gain a factor of 5 to 10 over other approaches in speed. So this is really the central result for MACE. And here is the thing that I told Christian about. So I plotted the average number of neighbors and the theoretical floating point per second. And I compare Nequip and MACE. So this is the ratio between the flops of MACE and Nequip and MACE. And you see that it grows with the average number of neighbors. So theoretically, you should gain more and more speed as you have more and more dense structures. So for a reference point, usually molecules with a standard cutoff is around 15 to 20 average number of neighbors. And then you can go to dense carbon, for example, and this can go to 80 or even 100. So really, in the molecule setting, you're expecting to gain a factor of 10 or between 5 and 10. And with cross-pack, you can go to even more, theoretically. Obviously, this is theoretical. I think Dominic has a question. Go.
Yeah, so since I had a question for the previous slide, but since we're here, like, I would like to ask, when you increase the number of neighbors here, like, we're talking, for example, when we want to do a simulation for protein, like force field for proteins, or like, are these realistic numbers in other molecular structures?
So yeah, so as I said, the average number of neighbors is really representative of the density. And for small molecules, the density, and it's also a function of the cutoff, but for reasonable cutoff, for small molecule, you're around 50 or 20, 15 or 20. So it's more here. So you're in the range of 10. And but for dense materials or very dense protein, I don't know for protein, but for carbon, for example, I know you can reach 80 or even 100.
Okay, but can you, like, is there any material that goes to 500, like, or
no, but this was to show the scaling. This was to show the saturation, the scaling. Yeah, it's
also,
not
it's just a matter of the cutoff. So if you take,
you can do 500.
You are easily there.
Yeah, because it's a matter of the cutoff. Okay. And
yeah, if you
go
take
at
12 angstrom in condensed carbon, you can do 300 easily. So
yeah, okay, makes sense. Depends on the cutoff. So here, how are you training on data at 300 Kelvin and testing on data at 600? Like, where does the temperature go into your model? Like, you train only at 300?
So when I prepared this data set, I was running MD at 3 different temperatures, and then I took independent samples from each of the 3 different temperatures, and then we use the 300 Kelvin data for training, and we use independent samples from 600 and 1200 Kelvin for testing.
But how does, like, if you never train on temperature variation, how can you expect any network to generalize there? Like, is this a realistic test to run? Shouldn't you, like, train on 600? And
no, actually,
I think you could. So if you weren't fit to do the best model, you would train on 600, 1200 Kelvin as well. But we created this to be a challenging test of extrapolation, kind of out of
but
distribution.
Extrapolation, like, there are many things that change when you change the temperature. How do you change the input of the network such that
you just have different geometry? So the only thing that changes the geometry.
Okay, this is my question basically, like how do you input the temperature to the model? Okay, so if it's via the geometry, then it makes sense.
Yeah, the geometry. So basically, if you expect that at 1200 K, you will have an average bond length a bit bigger, right? I don't know, confirmation that are a bit less from close to equilibrium, and I show that right here. So this is the this is the potential energy surface that David did with DFT of this 3-BPA molecule here, and then the white dots are the training data, and they are sampled. You see near equilibrium at 300 K, and then this line here is a 1D cut of this surface, and then it's also the black line here, and then we test MACE, and also other architecture, Equip and botnet, just train on these white dots, and we show that even if this curve, this 1D cut is very, very far from any training sample, MACE can reproduce very well the potential surface. So it really shows that it has captured, in some sense, the physics to a large extent of this small molecule. So really, this is a severe test, and it does it remarkably well. And then I want to, David mentioned a bit this paper, but the previous paper of that, and as David said, MACE didn't come up really just from tweaking and ad hoc, but it really came from our understanding, and in particular our understanding of ACE and other MPNNs. And we have created a unified formalism to explain most of ML potentials. And Leon, I think, has a question.
I had a question on the scaling of computational cost. You showed earlier roughly on how it scales as increasing the equivariance. How would it roughly scale by increasing the body order? Does it go exponentially if you increase body order? Because you get all these products of all different LM.
So I think with body order, what happens with body order is that you the size increases, but not really the costs, because the cost is always in evaluating the two-body, the edge features, and then you just form products. And depending on so I think it's not really it's not very expensive to go to high body order in that sense.
But so you're saying
it's
like
less expensive.
Sorry. So we're saying like parameter count goes exponentially up, but kind of computational cost not really, because it's dominated by different parts.
It's not going to be exponential. No, it's close to constant, basically. Formally, I think it's constant, but in practice, it's not quite.
Well, it depends on how you specify the basis. So it can be constant. So for example, in linear ACE, it's constant because you can pick up at each correlation order the same number of terms. Because really what explodes is the number of total terms, but really you will only create a subset of them. And so the kind of specification we do is on the total LM, so the total L of this correlation, and roughly it's a kind of truncation, and the truncation is more severe at each correlation order. So you take proportionally less and less terms, so the scaling won't be exponential. If you do the naive way and you create the correlation order with no specification, obviously it will be. But there is a truncation there. It's more severe to increase the L. The big L is more severe because this big L will be here. This H will have it, and this operation is on the edges, and this is really what kills you if you increase the what kills you. Like if you, it's really severe in that sense. It's again not exponential, but it's much severe.
Thanks so much.
Yeah, so I was talking about this other paper where we provide a theoretical tool to really systematically probe the design choices of ML potentials, and we wanted to identify also future paths of improvement. And this framework is called multi-ACE, and there is this paper in collaboration with the group of Boris Koryzynski and a related paper also by Chariotti groups. And really what we did is we classify most of the MPNN machine learning potentials architecture in the literature by the set of hyperparameter of the theory. And this set, David already covered it in some extent, but we added the number of layers because now we are not just in the ACE setting, but we also stack layers. And basically using this 5 hyperparameter, you can classify close to all the things in the literature. And here you have a lot of architectures. And really MACE is a new entry in this design space that is the first one to combine equivariance with higher order messages. And this is really what the reason of its effectiveness. And yeah, I encourage you to, if you're interested in the introducing yourself to the design space, to read this paper. It's very complete. And yeah, there are a lot of exciting challenges. Obviously, what we do is really local or semi-local, but how much does it learn semi-local information, and how much is it interesting to stack and stack layer for the receptive field, increasing the receptive field? This is a area of research right now, and very interesting. Also, theoretical understanding of equivariant messages and how it's related to the expressiveness proof that higher order message passing in the non-equivariant case that we had before. So I've seen one message like that in the chat to relate that to older higher order message passing networks. And really the interesting thing with MACE is that it's on the 3D space. So you have a new setting to interpret expressivity of higher order message passing in this setting. And it can be, and we answer parts of this question on the sparsification, but yeah, we need a new understanding of expressiveness. The most important thing is the code, because we released the code and it's on GitHub, ASUT MACE, and we encourage you to go and test out the code and read the 2 papers. And obviously, thanks to our supervisor, Gabor Chani, and also all the collaborators in these 2 works. And now we need to add the new papers coming up tomorrow also. Thanks a lot.
No, thank you. And yeah, I think you have a quite awesome list of co-authors there and also collaborators. Yeah, if anyone's interested in MACE, I think it's probably one of the more practical things that we're looking at. So yeah, you can have a look at the code, I suppose. And then from my side, a huge thank you.
Thank you.
Thank you.
Thank you a lot for presenting today. It's a great presentation, an awesome paper. As Hannes said, very practical and useful. And in terms of practicality and usefulness, I'd like really to know traditional methods. For example, if we take for computing this kind of forces, like if we take traditional force field, semi-empirical methods, for example, PM6 and DFT methods. So I would like to know, like, where does this method stands in terms of computation time? Is it faster than semi-empirical but slower than traditional force field? And does it perform better and worse than this kind of method? So I probably guess it's not as good as DFT because it's trained on DFT anyways, and it's much faster than DFT. How does it compare to other traditional methods of doing that?
Okay, I can take this. So what you need to think about, I think you have to separate 2 things. That is the kind of cost, and there is the scaling. So what we have with molecular mechanics, so empirical force fields, and with machine learning force fields like MACE, is a linear scaling with system size. Whereas DFT, like traditional DFT and something like PM6 or tight binding or semi-empirical quantum mechanics, they have they diagonalize a Hamiltonian, so they scale with the cube of the number of atoms. Okay, so I think this is one of the major things. So you will have a different, like this comparison will be different depending on the size of the system you are interested in. But like we can still discuss it in terms of actual speeds. And what you have is in molecular mechanics and empirical force fields is that you typically have for a force call, you should look at sub-microsecond times in wall clock time. And then with MACE, we are, I think, near a millisecond. So, you know, there is still a factor of 100 or 1,000 there. And I think with the semi-empirical models, you would be closer to hundreds of milliseconds. And then with DFT, you would be in the minutes or hours. So I think there is a, you know, maybe like a huge speed up going from DFT to MACE. And then there is an extra factor of 100-ish to go to molecular mechanics. So, and I think this is a huge challenge because a lot of the applications of empirical force fields are in molecular or medicinal chemistry simulations, and their sampling is really limiting the efficiency of the simulations, maybe even more than accuracy. So people are very unhappy about being slower. So it's a huge challenge for us to actually, you know, make something even faster. And that's definitely something we are working on to figure out how to, you know, approach this empirical force field speed. And this is not the case in materials science. So materials science, empirical force fields are so bad in a way that that people happily take the factor of 100 slower machine learning force fields and can do amazing science. But in medicinal chemistry or, you know, drug discovery, it's a lot more tricky. And as you can tell, a lot of the application papers that you can see in Nature or Science are from materials science rather than biochemistry for now. But it would be huge, and I think I'm definitely very motivated to tackle the drug discovery bit.
Awesome. So when you say that you have maybe 100 times improvement over semi-empirical method, that would be for small molecules that we're talking here?
I think even that,
yeah. So I guess this will grow to thousands and millions of times for bigger systems like
sure, if you want a whole protein.
Yeah, if you want a whole protein. Okay. Yeah, so right now your paper focused on small molecules. Is this because of the lack of data in other like in other areas, or like why did you specifically use small molecules?
I think this was the kind of most straightforward test case where there was a kind of standard benchmarks to compare against. But we are preparing another manuscript where we test it on many different systems, including battery electrolytes and amorphous carbon and liquid sulfur, and so, you know, all sorts of other things. Yeah, so internally we have been using MACE for a variety of systems. I think we have also used it even for a catalysis, heterogeneous catalysis, so small molecule reacting on surface. So yeah, this is all things we have done, and we are going to publish it soon. Maybe I mean, the aim is this year.
Yeah, so I think also if we talk about drug design, one of the biggest thing that's hard to simulate is like trajectories of proteins, like how proteins evolve through time. Like this is why we often work with crystallized structures of protein. And yeah, so do you think your method, since your method uses only a few layers, only a few layers and has only like the MPNN window that you can access, like can a method train on small molecules generalize to larger molecules like peptides or protein, because inherently the force field are the same? Or will you then face challenges because of the flexibility of the structure itself. Like, what's your take on that?
I think the challenge will not come from the flexibility of the structure, but the challenge will come from long-range interactions. So a lot of these systems are, so small molecule, the physics is very much local. But if you think about how a protein folds, then kind of van der Waals and Coulomb interactions, which are 1/r, so Coulomb in particular is 1/r in decay, those are very long range. So actually to model the folding of a protein, you can't really use just a local model, but you need a local model in combination with some kind of a physical description of long range interactions. So we are working on extensions of MACE with charges in various different ways, and even dipoles. And then, I mean, that the hope is that will, get there. But yeah, just MACE as it is, I wouldn't think it can correctly fold a protein just from this physical reason.
Yeah. Long range is the big challenge of the field right
now. No local machine learning model would be able to.
Yeah. It's really about short range models right now.
Yeah, I was talking more about like the protein that changes conformation over time rather than folding, but I guess same challenges.
It's the same, yeah.
Also face. Right, and so in terms of applicability, for example, like in RDKit, we can get force fields approximation using traditional methods. Like, how feasible would it be to kind of implement this kind of model directly into RDKit, and so people can just like get better conformation generation out of the box without having to rely on DFT methods.
I think this is I am very optimistic, and this is one of my main projects to give like to publish a MACE that can be plugged in. I mean, I was thinking more in OpenMM first, but obviously RDKit could also make use of it. But it's quite challenging because it has to be a model that is never too wrong, right? That's the one thing that the RDKit force field does. So that's quite tricky to actually ensure that your model is overall much better and never much worse. And I think the never much worse is a very tricky bit. Yeah.
Yeah, exactly. You don't want any nonsense. Well, you can always use the traditional RDKit to validate that you're not too far. Yeah, but you're right. Like, we don't want to give a toolbox that is sometimes very wrong, or at least have a measure of uncertainty. Like, tell the user, like, hey, this is the approximation of the force field, but don't trust it. Yeah. Okay. Thanks a lot. I think this covers all my question. It's a very exciting work, very practical work, and really eager to see this kind of force field, learned force field, catch up everywhere in the traditional MetCam world. Thank you.
Thank you. Thank you.
Thanks.